Welcome everybody to this week's Green Bank Observatory Community Zoom. We're looking forward to today's talk. Just a couple words about what's happening at the observatory. So the saga of the prime focus boom arm is now completed. As you were aware, there was an issue with the mechanism being jammed up. That's been all repaired, and we are back on the air with prime focus receivers. So many thanks to our telescope mechanics and Brian Jenkins and his team for getting that sorted out in record time. So that's great. Your proposals have been reviewed by the TAC. We now will meet in a week or two to finalize the dispositions, and so stay tuned for an update on that in a couple weeks. You should know the outcome of your proposal submissions. All right, with that, I'll hand it off to Jay Lockman to introduce today's speaker.
Okay, thanks, Jim. Our speaker today is Aya Keller from the University of California, Berkeley, and she'll be speaking on dark matter search using the GBT. And as usual, if you have questions, please submit them through the Q&A box on the lower right, and we will deal with them at the end of the presentation. It's all yours, Aya.
Hi, everyone. My name is Aya Keller, and I work with a group in UC-Berkeley, that searches for the axion. And just to give a very short introduction on axions, axions are dark matter candidates, or a dark matter candidate that actually solves two big problems in physics. So originally, it was actually proposed as a solution to the strong CP problem, which is a problem in particle physics, not even astronomy. And without going into the weeds of particle physics, the strong CP problem can be demonstrated with the lack of an electric dipole in a neutron. So we would expect that a neutron, which is made up of three quarks, would have some kind of electric dipole based on the angle between the quark alignment. And this hasn't been observed. In fact, it's been observed to be essentially zero. And scientists tend not to like quantities that just happen to be zero. And so in 1977, Pecci and Quinn proposed the axion as a solution. And basically the axion would be a field, a dynamic field that minimizes the angle between the quarks to the lowest energy configuration, making it zero. And then a year later, Frank Wilczek coined the term axion after the laundry detergent because he realized that it would clean up not just one problem, but two problems in physics. Also the dark matter problem, which is the problem that we don't understand the composition of the vast majority of the matter in the universe. And this matter is dark, meaning it doesn't interact electromagnetically or with regular matter, or if it does, it's very weak. So there have been so many experiments over the last few decades looking for different candidates for dark matter. And to this day, we have no idea what it is, and barely have been able to constrain any aspect of its nature. And the way usually these experiments work is that they custom build detectors for specific candidates, such as WIMPs, which are weakly interactive massive particles, or axions, and they're built to a specific mass or very small range of features for each candidate. And this can be hard because the broad theoretical framework for dark matter means that you would have to build hundreds and hundreds of these detectors just to cover a small range in the overall plane of the potential dark matter candidates. So we thought we should try to match the broad theoretical scope with a very general observational approach, which would rely on as few assumptions as possible. And so we have been working on an essentially model independent search technique, which means that we don't assume anything about the particle. In fact, it can even not be an axion. The only thing we assume is that it decays or annihilates in the halo, and that it just follows the phase space of the halo. And I'll go into this a little bit more later, but we do this using the GBT data from the Breakthrough Listen public data release. And it's very nice that we get so many spectra from all across the sky. Very useful for our search. So our procedure is made up of two parts. So the first part is based on the assumption that dark matter makes up a static halo, and our solar system is moving through this halo with some characteristic velocity. And there are different halo models that have been proposed. And one of the nice things about our search is that we can easily switch between them. So we actually tried it with a couple different halo models, such as NFW and Burkert, and it can be done with any proposed halo model. So because we're moving through this halo, any quasi-monochromatic radial line that's produced by either decay or annihilation of some kind of ultralight dark matter would have a Doppler shift in the frequency domain with respect to the sun's direction of motion. The second part of our analysis relies on the spatial distribution of dark matter represented by the standard halo model that we're using. And because of this, when we look into different areas of the galaxy, the line integrated density would change, and so the signal amplitude would change. And we're assuming that the amplitude is following this density. And then this is just a representation of two possible processes that we are looking for, so decay or annihilation. And then just a visual representation of the concepts I just described. So on the left here are two galactic plots. So on the very left, you can see that the sun is moving left through the galaxy. And so any of the targets that we're looking for in the forward cone are going to be Doppler shifted, are going to be upshifted in the frequency domain. And looking back, they're going to be downshifted in the frequency domain. And so in this plot here, you can see that we would see two separate Gaussians. Similarly, if we look into the center of the galaxy, the amplitude would be higher because of the higher density of dark matter in the center of the galaxy, as opposed to if we look out towards the outside of the galaxy. And in this plot here, you can see just the difference of amplitude in the Gaussians. And the way our procedure works is we actually subtract them. So we get two separate signature signals, one of which is antisymmetric and one of which is just a regular Gaussian. And then we can search the data in that way. And then just a couple of Mercator projections of the targets that we're using. So we did some fine tuning with which targets, which combinations give us the best results and the best sensitivity. So here are the forward and backward targets that we use, and here are the inward and outward targets that we use. So the data spans 3 years, and from the Breakthrough Listen public data release. It's very extensive in frequency. So we have the LS, C, and X bands. This little analysis that we did for the paper is just a small region in the L band. And we're working on currently the S band analysis, which spans the entire S band. And so you can see this, I guess you guys all probably know that there's a polyphase filter in the data. And we've struggled with this a lot to try to extract this filter. And eventually we constructed an ideal form of the filter that we just divided out. So the core of our analysis is normalizing all the spectra so that we can combine them in whatever way we want, because they all range in power and structure and all of this stuff. So basically we have to normalize them all to one without diluting the actual signal. So we've worked on this. We've tried many different techniques. What we came up with is a weighted polynomial method. So we fit two polynomials. And so here is an example of a signal that we would inject. So one of these polynomials is weighted, one of them is unweighted. So when we divide them out, the signal is still there in the normalized spectrum. Yeah, and then this is the flux density that we're using. Just has a bunch of telescope parameters and physics parameters. And similarly for decay, the difference between annihilation and decay is just a factor of square root of 2. And the integrand here is rho for decay and rho squared for annihilation. Otherwise, it's the same. So this is the Doppler analysis. That's what we call the first half of the analysis. This is where we create the asymmetry with the forward and the backward targets. And so we just average over all the forward targets and then average over all the backward targets and create this asymmetry, which is forward minus backward over forward plus backward. This is in this little plot on the top right is the ideal form of the signal after it has gone through all our procedures. So starting from the weighted polynomial and all of that stuff to the very end. So you can see it doesn't quite look like the two Gaussians because of the nature of polynomial fitting. But we have some kind of template that we run through the data. And this is the actual data with an injected signal. So it matches up pretty well. And all we do is just cross correlate them. And we get a peak where they match up. Similarly, for the intensity, the procedure follows in a pretty much analogous way. The only problem is we have to make these two analyses independent so we can combine them. So we have to take out the Doppler shift in the intensity analysis. So we have to match each inward and outward spectrum in terms of the angle in forward and backward. So we use a matching algorithm to make sure that they're selected in pairs. So the Doppler shift is always canceled out and the two Gaussians align perfectly. So again, in this case, it's a symmetric signal. And once again, we convolve it and we get a peak where it aligns with the signal. And then we can actually just combine them because we have ensured that they're independent. So we use a p-value analysis. And in order to actually set some kind of limits for our exclusion plot, we just inject signals going down in amplitude until we reach the 3 sigma limit. So that's where we say a signal of this size would not be detected, anymore by our procedure. So this is the exclusion plots that we ended up with for about 100 megahertz in the L band. This is for annihilation and decay, and we have both 1 photon final states and 2 photon final states. And this also includes a little factor of stimulated emission, which is another thing that I won't go into, but it improves our limits a little bit. And that's just a concept paper. So what we're doing now is actually applying this procedure to the entire S band to see if we can set some real limits. And the main problems that we're dealing with right now is just the minimizing the noise in the data, whether it's the polyphase filter or the larger structures. So any advice is welcome on that. And that's pretty much it.
Okay, okay, thank you very much. This is just a fascinating use of that data set. Let me remind everyone to submit questions through the Q&A box on the lower right of the screen. But I want to start by asking, you are tuned, if I understand it, you are tuning your analysis to the expectations of a line width that's based on the rotation of the Milky Way in a dark matter halo. So, but you would pick up any spectral line that was widely distributed. Is that correct?
Yeah, so the purpose of our subtraction is to cancel out any signals that are not Doppler shifted. So the only signals that should remain in theory are ones that are static.
Right, okay. And the, excuse me, and so, but I'm wondering how finely you are tuned. Let's say that I'm not thinking about axions now in an extensive dark matter halo, but rather some diffuse molecular gas that would be more concentrated to the inner galaxy. Well, of course, you could always inject a test signal that would mimic that and see exactly how sensitive your analysis was. But it seems to me you're casting a very wide net here that might turn up a lot of interesting things.
So if there was if there was a molecular line, it would be rotating with the galaxy.
Oh, I see. Okay.
Yeah, so it would, in theory, cancel out with our asymmetry.
Except in the forward toward the galactic center and anti-symmetric direction. Yeah.
Yeah, but yeah, I guess that's why we have the two analyses together.
Okay, and we do have a question here. Is it determined that the dark matter halo is static and that it doesn't rotate with the baryonic matter of the galaxy?
Yeah, that's a good question. It's pretty much the consensus is that it is static. Of course, we aren't sure about anything, but this is a good question. I can look up some publications that talk about this. But basically, halo models are made from simulations, numerical simulations that track the formation of the galaxy from the beginning, and that's how we come to the conclusion that it would be distributed in X, Y, Z way to achieve our final form where we are today.
Okay. Yeah. Let me just mention that we seem to be having a technical difficulty that's keeping a number of people from logging into this live. But just remind everyone that this is recorded and very shortly will go up on our website. So you can direct people there to view the presentation. Let me just see if there are any more questions at this time. So now we're waiting a minute. Let me just ask, you said that this was the sort of proof of concept paper that you just published. And what sort of expectation of the improvement would you get with the full data set?
Yeah, so we're trying some new normalization techniques. We are seeing some improvement. The problem is that the higher up we go in frequency, the less we have stimulated emission factors, and there are some differences in the signal amplitude. So it's hard to compare exactly what the limits are going to be like, but we expect them to be better than in the concept paper.
Okay.
Yeah.
Okay, we have one more question here back about the static halo. As a static gravitational force, would it not exhibit a drag on the rest of galactic matter? Sort of a dynamical friction, I guess.
So it doesn't interact with matter in a way that would cause friction because of the nature of dark matter, but it gravitationally definitely does slow down the galaxy. In fact, one of the reasons we know that dark matter exists is because the galaxy rotation curve follows, it is linear out as you go out in radius. So because there's more matter that we can't see in the center, it does slow down the rotation of the galaxy. If that makes sense.
Okay, well, thank you very much. Let me remind everyone again that this has been recorded and so will be able to be viewed on our website. And please join us again in 2 weeks when we will have Helen Kirk from the Herzberg Institute speaking on the Keystone Survey of Molecular Clouds. Look forward to seeing you then. Thank you and goodbye.